Okay, hello everyone. I'm Yao. It's close to lunch. I hope you're not very tired. And here I'm going to give a tutorial on how to generate the EPR file, the core database of Perturbo. I will use a silicon as a minimal example with a very coarse grid. And you can download this tutorial or lecture file from this link that I think Shelling has shared it already. You are encouraged to download this tutorial and follow it in the future. Maybe you may not catch while I'm running this code. And this Jinsu has introduced that Perturbo basically is doing like electron phonon stuff. We have like DFT calculation, DFPT calculation, Wannier90, and then combine all this output from these softwares. Perturbo is can calculate the electron phonon matrix elements and also the electron structure and phonon structure and interpolate it on ultra-fine momentum grid, which is very useful for the following dynamics calculation. And to be specific, to generate all the data files, all the data will be stored in the EPR file. And to generate this EPR file, there are like many steps. So I will walk you through this. The first one is you have from quantum espresso, you have like a self-consistent calculation first to get the ground state charge from density functional theory. And then you do NSF calculation to get the wave functions in the whole Boolean zone, which is useful for Wannierization. And then you have a Wannier90 code to construct the Wannier function from this wave function in momentum space. And then you have like, you also need to do density functional perturbation theory calculation using the pH.x. And this can also give you the phonon structure, give you the electron phonon matrix element on the coarse grid. Combine all these outputs, QE to perturb.x will read in all these files and generate the EPR file. And this EPR file will contain the bands, the tight band, the Wannier hopping parameter, the force constant of phonons, and the electron phonon matrix element in the Wannier basis. And once this EPR file is generated, Perturbo can read it and do the following calculations. Okay, and here I will use silicon, the minimum example. This is the crystal structure, and this is a band structure. I will Wannierize the 4 valence band and the 4 conduction bands. And this is the phonon dispersion. These colors are for the electron phonon coupling strings. Following this tutorial, you will be able to generate these results. Okay, first of all, let's set up the environment. You can do it anywhere, but I suggest you as a beginner to use Docker that we have prepared a very pre-download everything that you need to run this Perturbo-code. And you can check our website that Shelling has shared before. We'll not do that again. And first of all, let's launch the code that I have prepared script. Not launch the Docker. Wait a second. Okay. Now we are in this directory for silicons. Let's go into it. In this directory, we have SF, NSF, Wannier, phonon, QE to Perturbo, and also pseudo potential. Let's first do the SF calculation. Here we have an input file. This is a standard SF input file for silicon. You have prefix and also calculation mode. Calculation is SF. This means that the code will iterate over the charge density and converge it. And also output of the output directory for the pseudo potential, index for the Bravais lattice. This is a lattice constant. The unit is Bohr, not angstrom by default. Number of the unit cell, number of the atoms in the unit cell, number of types of atoms in the unit cell, and cutoff, playing with cutoff energy for the wave function, and also there is also crystal structure. And here I use a k-point list. It's quite coarse. It's 8 by 8 by 8. Okay, then we can write. This is very fast. I use the course grid for demonstration. This should take like 5 seconds. It is iteration over the charge density. Okay, the calculation finishes. The output is saved in the temp file. Let's go into it. And si.save file. Here we have some data here. Most importantly is this charge density. Most importantly is this charge density.hdf5. It contains a converter ground state charge density, which will be useful in the following calculation. Now we have you can actually also check the Quantum Espresso website for all the explanations for these parameters, how to write the input file for the PW.x. Okay. Now then we go to the NSF calculation. This is useful. I need to get the electronic state in the whole plenum. First of all, let's copy the charge density here from SF calculation. Then let's take a look at the NSF file. It's quite similar. It's quite similar to the SF input, except one difference is the calculation mode is NSF, means it will not iterate over the charge density. And here, n bands equals 16. This is 16. This is also important because if you don't set this calculation will only solve the electronic state that is occupied for insulators. But here I also want to include the conduction band. So I said you should also take your own research to find what's the number of bands that you need in your case. But here 16 is enough for me. And also there is a k-point list. This because I will use a 4x4x4 k grid, so it's in total 64, and this is a list of the k-point. This is total 64. How to generate this k-point list? You can follow Wannier90, and there is a very useful script called keymesh.pl, and this should be in the Wannier90 utility keymesh.pl. Yeah, you can download the Wannier90 and you can find this inside the Wannier90. And this is a script. This is a command, and you can get it. You can copy this to the NSF file. Okay. Now it's ready to do the calculation. Now it's solving for, now this code PWX is solving for different k-points. I have like 64 k-points. So it is looping over the k-point, and this part can be parallelized a lot because each k-point is individual calculation. This should take like 30 seconds. Okay, calculation finishes. Let's check the output file. It's still in the temp file. Save. Here we'll still have the charge density, and also we have the wave function file for each k-point. Here we have 64 k-point, so we have 64 wave functions. Okay, now this part finishes. Now it's ready to construct the Wannier function. Let's go to the Wannier function directory. And the first thing is to link the wave function here from the NSF calculation. Now there are two input files. One is si.win, another is pw2win.in. This is the core file. This is the input file for Wannier90. This is the input file for pw2wannier.x. Let's check the input file for Wannier. This part specifies the initial projection. I here it's a silicon for the 4 valence band for 4 conduction band is sp3 orbitals. Each silicon has 4 sp3 orbitals, and 2 atoms means in total of 8 Wannier functions. And also a number of bands, a number of the DFT band is 16. Should be consistent with your NSF calculation. And this part is about the disentanglement, how the energy, and also this is the energy windows, frozen energy windows. This frozen energy window will treat the 4 valence state and the first 2 conduction bands accurately, and the energy will be treated exactly. And this is a K-point grid. It's 4 by 4 by 4. This should be consistent with the NSF calculation. And this flag is right U matrix equals true. This is useful for Perturbo because Perturbo need to read in the unitary transformation matrix from the Wannierization step. And this flag is also useful, is also demanded by Perturbo. This will write the centers of each Wannier functions. And also you have a K-point list. This is exactly the same as the K-point list in the NSF calculation, except the last column is deleted. Okay. Let's also check the input file for the PW to Wannier90. This input file is will read by the PW to Wannier19.x. It will, because Wannier90 works for Wannier90, but the quantum espresso have some other files. So PW to Wannier19 code will read the output from quantum espresso and transform and calculate everything that is needed for the Wannierization step. So you should have like a output directory prefix. This should be consistent with your previous calculation. This is actually quite standard for most of the case, for most of case. And let's run it. I have prepared a script called run wannier.sh, but let me run it one by one. First is to prepare the Wannierization. And the second step is to transform all the data from quantum espresso to Wannier90. That's right. Okay. Okay, it finishes. Now the last step is do the actual Wannierization. It will iterate to get the Wannier function. Okay, it finishes. Let's see the output. Now we have the mean output is in this si.wout. Let's check it. It's very long file. Anyway, but on this file you can know whether you can check whether there is any error code here. If it finishes, it will show something like this, timing information, and also at the final, it will also print out the center of the Wannier function and the spread of the Wannier function. This spread should be quite small comparing to your grid size. For example, if you have a K grid size of 4 by 4 by 4, and your unit cell is something like maybe 5 angstrom. So 4 by 4 by 4 means for one direction your supercell size. I mean, it's doing a unit cell calculation, but the corresponding supercell size is like 4 times of your unit cell because 4 by 4 by 4 K grid. So it's something like 20 angstrom. And if your spread is like less than, it's like 2 angstrom, this means your Wannierization is trustworthy. And also, you have the unitary transformation matrix for Wannierization and disentanglement matrix, and the center of each Wannier function. And one thing to mention is that many people are interested to incorporate GW band structure in this for Wannier step, and you can find a tutorial in Wannier's tutorial book. it will walk you through how to incorporate GW band structure in Wannier function, and this is totally compatible with Perturbo. It's just a Wannier step. You can follow it. Okay, now we have constructed the Wannier function, which means we are able to interpolate the electronic state. But what about the phonon and the electron phonon? We need to do the density functional perturbation calculation. This is from, let's go to the phonon directory. There are three, oh, sorry, I have output here. There are two files. One is the input file for the phonon calculation. Another is a script to collect the deformation potential and the dynamical matrix. Let's look at, first of all, let's copy the chart density here. That's always the thing you need to do when you're doing Wannier spatial calculation in most of the case. And let's see the input file. The input file is actually quite simple because most of the setup most of the parameters have been set up in your SF calculation, and ph.x will read that in. Here we have like convergence threshold, and the prefix should be the same, and some flags like this, do the coupon one by one, and this is for non-metallic system. This is whether to correct directory for each coupon, output directory, and the name of the prefix or suffix for the deformation potential, and the file name for the dynamical matrix file. It should be the .xm format because this is needed by QE to Perturbo. There is also coupon list, this 2 by 2 by 2. This is a minimal grid for tutorial purpose, and I can run this, but this will take something like 3 minutes, so I will not run it. I've prepared one. Now we have assume that we have finished the calculation. We have a dynamical matrix file at 1 coupon, 2 coupon, 3 coupon, but total we have actually 8 coupon because 2 by 2 by 2. The reason is that the symmetry is imposed here, so the number of the coupon in the irreducible Boolean zone is only 3, and we have prepared a script called ph collect, and you can run it. After running it, it will generate a save file. In this save file, it collects the deformation potential, which is also the electron phonon matrix element, and for each coupon, and the dynamical matrix file, which has the force constant. Fourier transformation of this will give you force constant. Okay, now everything is prepared to generate EPR file. Let's go to the QE to Perturbo process. Okay, the first thing need to do, here we have an input file here, is for the QE to Perturbo.x. The first thing you need to do is to link every file that you have generated before to this directory. For example, one thing is the Wannier90. For Wannier90, you have the U matrix, the disentanglement U matrix, and the center of the Wannier function, and make a temp file, and also link the wave function here from the NSF. Link the wave function and link some DFT parameters that is set up in the si.xml. Now let's look at the QE to Perturbo input file. This is the input file. You have actually quite simple. You have prefix, the same as the previous calculation, output directory, phonon directory, and the number of the K points. It's K1, K2, K3 means X, Y, Z direction. It's 4 by 4 by 4. And the DFT bands in the NSF is 16, so it's 1 to 16. And number of Wannier function, same as the Wannierization step. And this L Wannier equals true means that the electronic state will be stored in the Wannier gauge. This can greatly save the memory, but you should make sure that your linearization is accurate to represent the actual electronic state. And you can actually check our website for the input for all the parameters that QE2Perturb has. For this case, it does not show all the parameters because it's not a very complicated case for silicons. For example, if you want to do like 2D system, we also support that, the system 2D. Like also we support alpha, polar alpha. This is for the polar material. And spin component, this is for if you are doing like including spin orbital coupling, or TDEP, if you are incorporating like harmonic phonons. We have all the flags for you. And let's write. Now it's ready to run the code. Okay, it's doing the job. It's for one coupon, and the second coupon takes longer because the number of the symmetric image is more. Now we have generated this EPR file. This is called SI EPR.h5. It is HDF5 format, so it is cross-platform. You can, once you generate this HDF file, you can download it anywhere, and you can open it from using HDF5 subroutines. And it's not human readable, but the format is you can check the format on our Perturbo website. I have prepared a link here. It has all the, for example, some basic data for the like atom, like lattice constant, like lattice vector, like number of symmetries, symmetry operators, like, and also the electronic Wannier. This contains the 4-pin parameters between Wannier functions. This is electron phonon matrix Wannier, contains the electron phonon matrix element in the Wannier basis, which you can use this to interpolate to momentum space. And force constant files. And okay. If you can also download, this is HDF5, so you can also download this HDF5 view software online. And you can use this to open the file that I just generated. This EPR file should be Perturbo Workshop tutorial 2 silicon QE2Perturbo SI. Okay, get it. And you can check the this is file. You have like basic data, some like the same thing. You can check it. Okay. But most convenient way is to use Perturbo. Okay. Now we have the EPR file, so it's ready to do some actual calculation. For example, the easiest one is listed in the Perturbo directory. It's band structure calculation, phonon dispersion, and electron phonon matrix element interpolation. Let's go to the first to get a band structure. The first thing you need to do in a Perturbo calculation, it is always to link the EPR file to your directory. Now we have it, and let's see the input file for the Perturbo. It's actually super simple. It's prefix SI and calculation mode bands and k-point list. And this is this file. It's also here. You see it. This k-point list is the format is like this is a number of lines in this k-point list, and this the first 3 are the high symmetry points, and this number is how many points is linearly interpolated between the neighbor 2 k-point, and it's ready to write. Okay, finishes. After calculation, generate some file like si.bands and si.bands.yaml file, and I have also prepared a Python script. This Python script is based on the post-processing library called Perturbo-py. And you write, and it save bands.jpg. Let's check what's that. Workshop. sorry, this one. Tutorial 2, silicon, Perturbo bands. Okay, that's this. We have it. And now, second one is phonon dispersion. Quite the same, but you should change the calculation mode to be pH phonon dispersion, and also the k-point list becomes q-point list. And the list I use is quite the same. It's just along the high symmetry path, and you should also link the Perturbo file, EPR file here. And right. Okay, finishes. Now we have this one has the phonon dispersion is stored in this si.pH dispersion and this YAML file. I also prepare a script to plot it. This is also based on Perturbo-Pi. Okay, then this pH dispersion.jpg contains the phonon dispersion. Let's check. Okay, even with 2 by 2 q-point list, it looks actually quite nice. Finally, let's get the electron phonon matrix element. First thing to do, link the EPR file here. And check the input file. The input file is actually quite the same, except now you have also k-point list and q-point list. You should also specify what's the band, electronic band that you want to consider for electron phonon coupling. Here the number is 2 to 4. This means you can count from bottom to top. This means this point. And let's check the bands. K-point list is gamma point, and the band range is 2 to 6. It's the valence band maximum. And also we have a q-point list. Q-point list is along I think it's along the high symmetry path. Okay, now it's ready to carry the calculation. It finishes, and the file is stored in this si.eph.mat.yaml or this si.eph.mat, and there is also Python script here based on Perturbo-Pi. You can plot it, and you will generate the eph.jpg. Let's check it. Okay, this is the electron phonon matrix element. This is the phonon band structure. The color bar is the electron phonon matrix element. Okay, so I think all the calculation finishes. One thing to mention is that you can find that once you have generated the EPR file, the Perturbo workflow to get the to carry out the actual calculation is actually quite simple. Yeah, it's quite user friendly, I think, Yeah. That's all.